All right, here's the problem we're going to work on. It's called the Josephus Problem. The Josephus Problem works like this. Josephus was a Jewish general back in the period of time around the beginning of the Common Era, and he was a historian, and he wrote all about the wars and the very, very interesting period of time around the birth of Christianity and when Judaism changed its character. It's a really fascinating part of history, but we're not going to talk about the history of it today. We're going to talk about the math. And in one of his books, he has a little description of this particular game or puzzle, where basically there are people in a circle, and you want to determine which person gets saved from death. And you do every other person, pulling them out of the circle and sending them off to be executed. And you continue around the circle, pulling out every other person until there's one person left, and that person is the one who is saved. So Josephus, as he tells the story, made sure that he was in the right place, and hence we have all these nice history books. It's a good story. A lot of Josephus stories are good stories, and history back then is not as clear as history is today. It wasn't such a discipline. And it's all an interesting question about how history, well, historiography as it's changed back from ancient times till now. But we're going to do this puzzle, and what we're going to do, now that Joe's come, now I got 31 people in this room.
And his name is Joe.
And his name is Joe. Here, Joe, sit in spot number 15. You'd like to know, if there's a certain number of people in the circle, where to sit, right? Especially if you find yourself, sent back in a time machine where all your clever methods of persuasion are not going to get you out of some barbaric Roman deciding that you have to play the circle game and you want to sit in the right spot. So how do you decide? We're going to solve this problem. You give me a number, I'll tell you where to sit. All right, and we can do it quickly here. It doesn't take too long to actually do this puzzle. So let's assume that we'll go left to right. I'll tell you that if there are 31 people, you want to sit in spot 15. Okay, for example. And I think we have 31 people, so the 15th spot, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So Tom gets saved. Do we have actually 31? Let's just double check. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15, 16. Okay, but we want to include, all right. So here we go. Here's what you do if you're dead. Just put your head down on the desk if you're dead. All right, so we'll do every other person. You're not dead yet. You're number 1. It's the even numbers. Right. Dead, dead, dead. This is the fun part of the job, is pointing at people and saying dead, 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 dead. Now let's make sure we got the right order here. We'll just go to the back third row. So Andrew, you're next. Dead, dead. I need to know who's dead because I won't know next time. EJ. Okay, now we're going to go around this way. So Blake, Rob, Joe. Okay, now we're coming back around. So you got skipped. So Mike. Oh, I'm skip. I didn't include Alex in the number. Who's?
Me.
Okay, you're next.
Yep.
Next. Who's still? Sham.
Sharon shouldn't have died
No,
there.
Sharon's not dead.
Because Doug's already dead.
Yeah.
Oh. Sharon's safe, so Sham's dead. Who's? Anthony, you're dead. Who's next? Peter's still alive?
No, Peter's.
Now Peter's dead?
Not anymore.
Gary's dead? Baruch's dead? Chris is dead? Anthony, you're going to kill this. I can see this is out of control. All right. All right. Yeah.
If there are 31 people, it's number 31 who's going to be alive.
There's 36 people.
Are there 36 people now?
There are
31.
There's 31 people now?
Then it's
No,
31.
we have 31. He said number 15 was there.
No, number 15 would stay alive.
We'll find
I'm
out.
pretty sure. All right, so I can see this is getting a little chaotic. Let's go on the board here. Let's do this puzzle with 7 people. I had so much fun. I don't have to think. Give me a few minutes off. Let's do this puzzle with 7.
It'll be 7.
That's true. 2 gets killed. 4 gets killed. 6 gets killed. Who gets killed next? 1. Who gets killed next? 5. Who gets killed next? 3. So 7 is alive. Let's do another example. Make sure everybody gets it. I can't do 31. It's long. I'll do 11. Okay.
It's odd, I guess it's odd number.
7 will survive? I think 3 should survive. Let's see. 2, 4, 6, 8, 10. Now what? 1, 5, 9. Oh, no, you're right. 3 and 11. 7 survives.
31 is 31.
Yeah, but that's... Oh, no, I was wrong. It should be 7. Oh, I'm now 31. Yeah, I did 31 wrong. What did I say? No, 37. I did wrong.
31 you said.
31 you said 15.
31 I said 15. 31 should be 31. You're right. You're right.
Really dead.
Yeah. Okay, well, what is it?
Oh, you're dead.
Oh, it's me.
Jackson loses on the recount.
Right. There's actually, right. Josephus has another story all about how a particular general was going to be elected, but of course they lost the ballot, so they had to do a recount, and they just killed the person who asked for a recount. No, I made that up. It's completely not true. But it'd be a better story. Yeah, let's see how we can handle this recurrence equation. We could fiddle with this all day long looking for angles, but I'm going to show you one particular angle that really gives us a lot of leverage. And then from there, we're going to write down some data. We're going to make a good guess because we'll be able to see what the pattern looks like, and then we'll prove that guess by induction. That's our plan. All right, so first let's get a little leverage on this problem. I'm going to go back to the 7 case.
It's always an odd number.
Of course. All the evens taken out of the first round.
In the case of 2, but
All the
doesn't
evens are taken out in the first round, so it has to be an odd number.
doesn't this problem have a variant like with 3? I mean, you could get.
Oh, there's a lot of different variations of this problem, right? This is one variation of the Josephus problem, right?
Is it always odd number in the set that you start with, or it depends on the number of skips you do?
It depends on the number of skips you do. It depends on where you start. But let's assume we're doing just the problem where you go every other one. And in that case, you don't get any even numbers ever staying alive. The question is what happens after that. So we did this example before. And when you do this example, you all know, I can knock them off here. 2, 4, 6. We'll do it again. 1, 5, 3, and then 7's left. All right, so let's just write that down. We'll call J of 7 equals 7. That means if there's 7 people, the 7th one is saved. Okay? Now, what I want to examine here is the following interesting angle. Let's consider a number of people that's double this. And the reason we're going to do that, where's the motivation for that, is because after we finish one cycle, as Baruch just implied, half the people are gone. And the problem looks very much like it looks at the beginning, except the people are renumbered. Okay, let's see what I mean by this. So let's try 14. Let me try that again. It looks so bad. That looks a little better. Okay. Well, let's cross these out, but stop halfway. 2 goes, 4 goes, 6 goes, 8 goes, 10 goes, 12 goes, 14 goes, and now we are right here, ready to skip over 1. This is right where we were at the beginning. It's the same problem again. right? Recursion, induction. It's the same problem again, except now how many people are in my 7 people in my list, but they're not numbered 1, 2, 3, 4, 5, 6, 7. Now they're numbered 1, 3, 5, 7, 9, 11, 13. But you know which one of these is going to end up being saved. It's the 13th guy, right? The guy numbered 13 because he's the same as the one that we called 7 here. So if I knew that the answer for the 7 person was 7, that would imply that the answer for the 14th person is going to be 13. What I need now is a way to write this down formally in general. So before I do, let's say that for the 7th person, the answer would have been 5 is saved. What would that have corresponded to here? Would have corresponded to 9.
And what if we had 21
Ah.
there instead of 14?
That's a different problem.
That's different.
That's different. So
Right.
it's not multiples of 7. It's
We'll get to that. This works when we start with an even number. When we start with an odd number, there's a little bit of a twist, and that's a good thing to think about. We'll think about it in a second. What I want to do now is write down what we've just done in general, to take what we've noticed logically and turn it into an equation which is just 6 symbols long that looks like a recurrence equation. So here's what it looks like. If you take something that's an even number and you want to know which person is saved, that is j of 2n. Okay, we want to know what this equals. You go through the stage and you cut off all the even numbers, and now you look at what's left, and it's half the numbers left, and you ask yourself, what is that? What is the person that's saved in half the numbers? And you go over here and it tells you it's the number 7. And now you want to take that answer and transfer it back to the numbers here. How do you transfer it back? If it's 7, it turns to 13. If it's 5, it turns to 9. Right, what's the connection? Twice this minus 1. And that's not an accident, because that's what these numbers are. Right? The numbers here are doubled over there, and then it's just the one before it. So let's write this down. Figure out the answer to your half-size problem, multiply it by 2, and subtract 1. That is the general summary of what we just noticed by stopping after the first round and relating the Josephus problem for 2n to the Josephus problem for n. We can try this out on a couple more examples, but before we do, I want to do the example where it is an odd case, the thing that Doug just asked. Okay, so before I do that, are there questions? This is the most complicated part of the whole lecture today, the part I just did, the part that makes this equation. If you get it, then it's coasting down here. Then it's Heartbreak Hill, and you just got 3 miles down to the finish line.
You're not requiring that n be odd. N might be a power.
Here?
N might be to the n.
And
Eventually n will come to 4.
Here, n could be anything.
But n
N could be odd, right. That's why we need an equation for the odd cases, and we're going to do that right now. Let's do the same thing here and come up with a similar relationship. Here we have an odd number. Okay, so we cross out 2, 4, 6, 8, 10, 12, 14. Right? And now 1 gets crossed out. But then we want to, this doesn't work out so easily, right? We'd like to start right before 1, but now we have to, so now I'm here to start the next one. What happens now? So this would be like 1 in the new problem.
2jn plus 1.
And this would be like 2. And this would be like 3. So if the answer for this new problem is 1, then we want the answer to our problem to be 3. If the answer to this new half-size problem is 2, then the answer here should be 5. So you want to take this number. I'll write them down here. 1, 2, 3, 4, 5, 6. What's the relationship between these numbers, 1, 2, 3, 4, 5, and the numbers that we're going to have to write down for our answer? They're twice plus 1. And this part here, how many elements do we have here relative to 2m plus 1? We have n elements. We started with 15, 2 times 7 plus 1, and what's left? Should be 7 elements left. 1, 2, 3, 4, 5, 6, 7, because we did half of them off and the extra one at top. So we again have jn, that's nice, but this time we multiply by 2, 2 times 1, and we add 1. 2 times 2, add 1, and add 1. Here are the two relationships we get. These relationships are gotten by inspecting this idea and knowing that this angle would leverage us this nice, cool relationship. I should mention to you that you could stare at this problem a long time before you realize this idea and before you thought of it. So what would make you think of it? Again, you always want to think of a problem in terms of a smaller problem. So you're looking and you're hoping that you can do a little bit of work on here and make it look like a smaller problem. If you have that as a goal, it is not too much of a leap to go once around and then start to scratch your head and say, okay, I pretty much have what I started with here. How do I milk that into something? And if you have that as a goal, then this comes next. All right, so now that I've tried to motivate it, here it is. Here's our recurrence equations. And now we can look at some base cases, and we could actually build up from the bottom up some tables and see if we can come up with some kind of formula. And that's what we'll do right now. All right, so let's make a table. J of n. Here's n. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, if we have one person, who dies or who gets saved?
1.
1. If we have 2 people, who get saved? 1. Now I think we can use this recurrence equation. Why couldn't I use it just by, well, maybe I could have just used it. Could I have, do I need 1 base case or 2 base cases? That's the question. This works for even cases, and it works on the one that's half its size, right? This works on odd cases, working on one that's a little less than half its size. So 2 is going to depend on 1. Does it work?
Yeah.
So I didn't really need to do this as a base case. I could have done it as from my recurrence case. What about 3? 3 is in this spot, and it depends on 1. So 2 times 1 plus 1 is... All right, let's fill out some more. What's 4 going to be? 4 is even. So it's twice the 2 case minus 1. Yeah.
Did I understand correctly that you said you only really need...
We only need 1 base case.
Okay.
Right. 4 is going to be what?
1.
Everybody see how to get that? J of 4 is going to be J of 2, which is 1. 2 times 1 minus 1 is 1. All right, let's fill this in. Who's got some more values? You can just use either one of these equations depending on whether it's even or odd. That takes care of all the possible numbers. So if it's 5, you want to use this one. For 6, you'll use that one.
Yeah, so 5 is 3.
6 is...
5. 3.
I did this before, so let me check, make sure we get it right. 3, and this comes out to be 5. We know that 7 turns out to be 7.
Why are you not plugging n into the formula to generate it?
Because we don't have a formula that takes n. We have a formula for j of n that relates to j of n.
Oh, okay.
We have j of n in terms of itself. So we have to just use this column. We'd like to be able to plug n and get a straight answer. That's our goal. And we're going to get that soon. So 8 is going to depend on 4, right?
Could we do substitution and solve this recurrence equation right now? Or
We could try to solve this, but look, we've got these 2 cases. So we'd have to do a substitution and then back substitute the other way, and maybe we'd get something nice. We would. I mean, we could do it. But we're not going to do it that way today. We're going to try to avoid that. Because the closed form for this is really horribly ugly. And if we just look at it in a more logical way and prove it by induction, we're going to get a formula that's really much nicer.
Every time we have a j of an odd number, it's 2 more than the j of even.
Okay, so then 9 is going to be 9? Is that what you say?
The odd is 2 more than the even.
Oh, okay.
7 is
So let's get 8. 8 is 1, so 9 is going to be 3. 10 is going to be 5.
7.
11 is going to be
11 is 7 because it's 2 more than 10.
and 12 is going to be
4 more than 10. 9, 11.
How do you get the even?
Look at that. So isn't this
So we repeat a sequence of odd numbers that
good?
comes up to the
1, 1, 3, 1, 3, 5, whoop. 1, 3, 5, 7, 9, 11, 13. Look at these repeated sequences of odd numbers. They repeat at different sizes, right? Here we have 1, here we have 2, here we have 4, here we have 7.
to 15.
15.
I should go on, huh, to see when it goes back to 1. Let's just do that to make sure, since you're all convinced that'd be a good idea. 15 and 16 I'll do. 15 is going to be 15, and 16 is going to be 1. So that's where it really ends. 1, 2, 4, 8. 2 to the end, right. It's doubling every time. So let's try to write down some description that will let us figure out J of n based on what we know. And then we'll try to prove that description by induction without ever dealing with the substitution idea and killing ourselves. Okay? And how do you know when to do these things? You don't. That's what ingenuity is all about. You try different things. I wanted to show you this as just another example of a recurrence equation that yields to a different attack. All right, let's try to write down what this means. We need a conjecture. Anyone have an idea?
Well, we're starting over again every time we hit 2 to the k.
We're starting over again every time we hit 2 to the k. That's true. So then why don't I...
And from then on, it's 1, 3, 5, 7, 9, 11 until we hit the future k plus 1.
Okay. Let me try to write that out in a way that we can summarize. This says that if you want to know who's the survivor in any number that you can write in 2 pieces, here's the biggest power of 2, and here's what's left over after that biggest power of 2. Okay, because you said we restart after every power of 2. So figure out the biggest power of 2, figure out what's left over, and when you get that amount that's left over, you take that amount, say it's the second one, it's the third one, the fourth one, you want to get odd numbers from the 1, 2, 3, 4. So you want to take that number. If there's... Let's say you end up right at the power of 2. So there's nothing left over. Then your answer should be 1. Let's say there's 1 left over after the power of 2. Then your answer should be 3. If there's 2 left over after the power of 2, your answer should be 5. Figure out what's left over after your power of 2, and then multiply it by 2 and add 1. That's our conjecture. It's more than a conjecture. It almost screams that it's got to be true. It's way too coincidental for these odd numbers to show up. But let me review this again. We notice that it starts repeating after powers of 2. So let's go down to the powers of 2. Here's the first power of 2 that occurs. If there's nothing left over, if there's 0 left over there, then our answer is right there. Here's the next power of 2 that occurs. That would be 0. Here's the next power of 2 that occurs. That would be 0 left over. Those are all the values for the p's.
We want the dotted lines to be just under the power of 2. It should be under. No.
That's what I did.
One above it.
I should have one here.
Between 1 and 2, between 3 and 4, between 6
Here's
and
2, 4, 8.
Right, but I'd like you to put a yarmulke on the 8 rather than
A yarmulke on the 8.
put the
on the left,
12p8.
on the n column.
Here?
1 unit
On the
up.
n column.
Here?
That's it.
That's where you want it?
That's what I wanted.
All right. Well, I got solid lines there. But here's fine. You can put them anywhere you like. But the idea is that when you're done with a power of 2, you want to figure out how much is left over. If there's 1 left over after that, that means the answer is 3. If there's 2 left over after that, it means the answer is 5. So go to the power of 2 that you know is the biggest power in your number and start counting after that. As many slots as there are after that, twice that many plus 1 is your answer. Okay? So if you're in the 3rd slot after a power of 2, 1, 2, 3, your answer is 7. 2 times 3 plus 1. This is a conjecture. We have to still prove it. And we're going to prove it by induction. Because proving it any other way just seems like it's just going to be impossible. How are we going to get this from scratch? It's just might not be so easy. But by induction, it's going to be really easy. And we're going to prove this is true. Then we're going to notice something really cool about this problem. Then we're going to let it go and do some other induction problems. All right, questions about it? All right, so let's, now that we've got this, let's sure everybody knows how to use it. I want to make sure. Let's say there are 129 people. 129 people. 128 is the biggest power of 2. The leftover is 1. That means you're 1 past the biggest power of 2. That means you're 1 past one of these dotted lines. That means your answer is 3. Take 129, divide it into a power of 2 that's biggest, 128. 128 plus 1. The p is 1. 2 times 1 plus 1 gives you 3. So you want to sit in the 3rd spot. And if I asked you 2 times 120, the biggest power of 2 is 64.
113.
56 is the difference, is the p. Twice 56 is 112. Add 1, 113. So if there's 120 people, you want to sit more to the end. Well, it's a circle.
You get partial credit if you're
You got partial credit. You got partial credit if you're sitting right next. Yeah. You want to sit next to the guy who's sitting in 113. I'll be right next to him, 112. Do I get partial credit? Whoa, I'm getting killed in the 1st round. Here's what we want to prove, that this is true. Okay, we want to prove that this is true for any value of n. This is what we want to prove. And we don't have any slight idea why it's true. We just picked it out of this pattern. Well, that's cool, because we can do experimenting and find patterns. But we do know that this is true, and we do know that this is true. So if we try to prove this by induction, we can assume that this formula is true for smaller cases. And we have to show that it's true for the next case. That's what we're going to try to do. Now, in doing this, here's what we're going to do. We're going to assume, well, we want to show that this is true, and we'll assume it's true. Assume that it's true. Yes.
So the theorem, wouldn't it be easier to just write j log base 2 of n plus p equals 2p plus 1? Because then it's in terms of n. It's in terms of the n that you're trying to...
I'd have to take the floor of it and get the remainder of it. There's a reason I write it this way. It would really be much uglier if I wrote it the other way. This is a much easier way to write it. You're right, Anthony. You could try to do it with logs and floors, but you have to get the remainder of that log. It's not the log number itself. It's what's left over after you take the log.
Oh, there's no
It's the mod.
Yeah, it's the mod.
Yeah, it'd be ugly. Let's assume this is true for smaller cases. For smaller cases than n. A lot of you are used in induction of going from n to n plus 1. But it's completely the same to go from anything less than n to n. You just want to go from the smaller cases to the bigger cases. So I'm going to assume this is true for all the smaller cases than n, and I'm going to show that it's true for n. That's sometimes called strong induction. I'm assuming it's true for all the smaller cases, not just the one immediately below me, not just the n minus 1th case, but for all of them. And in order to do this, we have to show that this formula is true. And since this helpful relationship has 2 cases, even and odd, I'm probably going to have my induction have 2 cases, even and odd. So let's try the following. N is even, and we'll do here n is odd. n is what we call 2 to the m plus p. Okay? We want to show that this thing's going to be true for any n in the world. I'm going to assume it's true for smaller values of n. I'm going to assume these two things are true. I want to get this formula being true. All right, who's with me so far? Yes? Raise your hand if you're really with me so far. I want to see how many people are thinking. Yeah.
I just feel that the m's not rigorous. That you would have to somehow state there that m has to be the greatest. I mean, we're kind of verbally doing it, but I mean, that wouldn't be
Here.
That wouldn't actually.
Now it's rigorous. Okay? I think it's rigorous. Right?
Yeah.
So it has to be written like this, where p is the smallest. P is smaller than the biggest power. But you're right, Anthony. I have to be careful what I mean by this. Right? It just, you all know what I mean, but I should write it. Well, maybe you don't all know what I mean. I mean, take the biggest power of 2 and see what's left. Now you know what I mean. All right. Let's try to do this. Here's what we get. We're assuming n is even now, so that this is even. We want to show that this equals 2p plus 1. We can't use this formula. We can only use it if we have smaller cases. Well, let's take this and turn it into something that's a smaller case, and then use this formula. How do you take this and turn it into a smaller case? It's built in for us. Here it is. This tells us how to turn it into a smaller case. All right, so what do we get? We get 2 times j of half of this plus 1. Sorry, minus 1. How do you write half of this? 2 to the m minus 1 plus p over 2.
P is even.
No, p's even, right. So we can, p over 2 might be odd, but p is even, right. Okay, what's next? This looks like a horrible mess, right? Ugh. Right, this is a smaller case. Everyone agree that the 2 to the m minus 1 plus p over 2 is smaller than this one? Because it's half the size. So now I get to use my induction assumption to go to my formula. Okay? I get to use this. That's the whole idea of induction. Take what you start with, turn it into something that's a smaller case, using a relationship that you can get either through a recurrence equation or through some other argument. Use your induction on the smaller case, and then move on. So let's do the induction on the smaller case. What does the formula tell us? Here's the highest power of 2. Here's the leftover. It tells us that we're going to get 2 times this leftover plus 1.
So it's p plus 1.
2 times this is p plus 1 minus 1. 2p plus 2 minus 1, that better be 2p plus 1. Good. That's what we want. We want this to be 2p plus 1, and it is. So I've proved that when this number is even, if I start here, I end up here. There's 2 steps in the proof. One is using my recurrence relationship to get it into a smaller case. The next step is using my induction assumption. That's the whole power of induction. That's where the whole proof becomes easy. And then I just simplify it, and I get my conclusion. Yeah, Joe?
Could you just show the algebra on that? I don't understand what happened, like 2 to the n minus 1.
The algebra from here to here?
Yeah.
Look at this. This says j to the 2m minus 1 plus p over 2. 2 to the m minus 1 is the biggest power. P over 2 is the leftover. And the formula says multiply the leftover by 2 and add 1. The leftover is p over 2. 2 times p over 2 is p. Add 1 is p plus 1. And that's why I have p plus 1 in place of that. Does that make sense?
Yeah.
We never proved our recurrence relation, really, did we?
Well,
But we can use it? Or was that a full?
I think, well, we proved it enough, I think. I didn't write a formal proof on the board, but I think I convinced everybody that it was true.
But the point of this inductive proof isn't to prove that we're correct.
No, we're assuming these are true. We're assuming these are
We're
true.
proving that.
We're proving this.
Whatever equation.
This is what we're proving. Absolutely, right. You could prove the pair of these by induction. You could. And it would require some argument similar to the one we did. But I think you could also prove it just straight. These two don't scream out for induction like this one does.
They don't, even though you have an n case and an n plus 1 case.
Yeah, well, they don't, because when I explain the idea that makes these two formulas come up, there was nothing in particular about the idea that doesn't work in general. Give me a circle, I go around once, and that's the recurrence equation. It's right there. So there's really no need to go to smaller cases. In other words, there's nothing hard that happens as you go from the nth over 2 cases to the n cases. The only thing that's hard is you go around the circle once. Here, it's a little trickier. I don't know. I mean, it's a subjective thing whether a proof screams to do it by induction or not. All right, let's do this one for 2m plus p being odd. Which one of these things apply? This one applies. So we get that this equals to 2j something plus 1. Now, we need to get the right value here, right? This is 2 times something plus 1, and we need that something here. If we write this as 2 times something plus 1, what do we get here in the parentheses?
2 to the n minus 1.
All right, since I know n is odd, I'm just going to let p be an odd number too, because I know this number is even. So p is some odd number, 2 times k plus 1. And now I can write it a little more easily. So this equals 2 to the m plus 2k plus 1. Okay, this equals 2 times 2 to the m minus 1 plus k plus 1. 2 times something plus 1. So here's the something. Okay? And k, if you want to calculate what it is p minus 1 over 2. All right, let's go through the next step of the induction proof. We're going to assume this works by induction. Here's a leftover. We get twice this leftover plus 1. Twice this k, 2 times, twice the k plus 1. The k is p minus 1 over 2. So when you multiply it by 2, you get p minus 1. P minus 1 plus 1 is p. So again, you end up with 2p plus 1. It's the same proof as before. There's some details in the algebra you need to work through. The easiest way, I think, to see it is to write p as 2k plus 1. Remember Sam came up with a really cool way of thinking of our Chinese ring problem with binary numbers? If you do the same thing here and write out the j of n's for binary numbers, you'd also notice a pattern, different from the odd numbers. A pattern that just has to do with binary numbers, and that, you'll see, makes a lot of sense. But since we're doing computer science and binary numbers come up all the time, I thought this would be a neat thing to show you. And then we're going to move on and do some more proofs by induction and finish off the topic. Rob, you have a question?
Aren't you going to write those in binary?
I am. I'm going to write the j of n's in binary.
Write the ends in binary.
Write the n's in binary too?
Sure.
I have a theory.
You have a theory? If you have a theory, we'll do it. 1. Okay, what do I get here?
You're standing in the way, so I can't see. 1 1 101 111 1. do is you take the number on the left and pick it on the right, and that'll give it to you. The digit on the left.
My theory's vigor did not hold up to n exceeding 5.
But it's a good engineering story. It works for all practical cases.
Right.
Maybe we need to see some bigger cases to see really what's going on, but Sam has already found the pattern.
But that stems from the formula. Sorry.
Yes, yes. You're right, and you're right, and you're right. But let's write up a couple. Yes. Here, let's do this. Here's n. Here's j of n. Let's go from here's 7. Here's 14. 7 is 1, 1, 1. 14 is
1, 1, 1,
1, 1. Oh, whoops. I promised I would do this. 1, 1, 1. 1, 1. How do you write 14? 1, 1, 0. Oh, right?
1, 1, 1, 0.
Right, 1, 1, 1, 0. Good, because otherwise the pattern wouldn't work. All right, so Sam noticed the following pattern. He says if you take this number here, your n, your binary number, and you just take the leftmost bit and pull it around to the right end, you get your answer. Let's see if it's true. If you take this and you cyclically shift it, cyclical shifting is one of the typical built-in machine language commands in any processor. Shift your bits left. Right? It's easy to build a circuit that does cyclical shifting. You could write a Boolean algebra formula to take 3 bits and shift them cyclically. 3 come in, 3 come out. Okay? It could have been on a test. It wasn't. What happens here? You shift this over, you get 1. You shift this over, you get the same. You shift this over, you get 1. You shift this over, you get 0, 1, 1. You shift this over, you get 1, 0, 1. You shift this over, you get 1, 1, 1. You shift this over, you get 1 again. Look over here, 1, 1, 1, 0. You shift the 1 over, you get 1, 1, 0, 1. If you just showed this pattern of bits and said these relate to these, you might be able to notice that they relate by a left cyclical shift, without knowing anything about the recurrence relations or seeing anything else. This cyclical left shift corresponds to this rule. Let's understand why. What happens when you do a cyclical left shift to a number? Let's say the number starts with a 1, which it always does. We don't have any leading zeros. When you do a cyclical left shift, what are you doing to the number?
First, you're taking away the highest power of 2.
Okay.
Then you're doubling the remainder, which means you're shifting it over.
Shifting over 1 to the left means doubling the number.
And then you're adding 1.
And then adding 1. Take off the biggest power of 2. Strip off the 1. You're left with p. Take your p, double it, shift it over 1 spot. Remember, base 10, you multiply by 10 when you shift over 1 spot. Base 2, when you shift over 1 spot and put a 0 on the end, you double it. If you take that 0 and turn it into a 1, you've doubled it and added 1. This part takes off the leftmost bit. This part doubles it by shifting it to the left. This part puts a 1 in its place. And you'll notice we always have a 1 on the left end, so shifting it cyclically is always going to accomplish adding that 1. And that's why left cyclical shifting is the exact same thing as pulling off the 1, pushing it over 1 spot, and putting a 1 on the right end.
Although with the computer, if you've got 1, it's not actually going to be just 1 bit.
The computer, we'd have to do some issues here because it would have some fixed number of bits. There'd be zeros lined up here. We'd have to write some kind of code to strip away those zeros and move this to the left in the byte. It would be a little bit trickier to actually implement it on a computer.
The
and you're right.
machine code that you said that's in most processors wouldn't strip off the zeros, would it?
No, but we could do this and then mask it through using those logical AND kind of things and pull out the bits we want and put them in new bytes. You could do that. It could be done. All right, questions about this? In recitation today, Tara will do some more inductive proofs. review any questions you have in the problem set on recurrence equations or recursion, and then we start new topic tomorrow, counting. One example that I want to do today, well, all the examples I'm going to do relate to computer science in one way or another. One example is a really brief example, a 2-minute example that has to do with the correctness of programs, showing that they actually do what they're supposed to. Another example has to do with binary trees and how to count the nodes at the bottom, the ones that are called leaves. Another example has to do with some number theory that will eventually lead into cryptography, and it's similar to a problem you've already seen before in a problem set. I'm just going to present it in a way that shows you how to do it in general, and we're going to nail that problem down the last week of class in much more detail. So all these things will be things you'll see again and you've seen before as well. So first thing, proving programs are correct. This is a big area of research, and it'd be nice to prove that your loops do what you think they're going to do. So there's a lot of work that goes on here. How do you describe what it is that your program's supposed to be doing? Once you describe it, how do you formally prove that it does what it's supposed to do? When you have loops, you do what's called loop invariance. You say what's supposed to be true about the loop with respect to the index of the loop, and then you prove by induction that that thing stays true. It's really dry, and I won't do an example. The book has some examples, but that's how that's done. The other way that it's done is for recursive programs. Recursive programs, it's just completely transparent how to prove that they work. They work because they're recursive, and you do a mathematical induction proof on the recursion. So here's an example. Let's say you have a binary tree, and you want to sum up the nodes. To sum up the nodes in a binary tree. Here's a picture of a binary tree. You've got a root, you got a left subtree, and you have a right subtree. These are each trees themselves. If you remember from a month ago in Scheme, you can represent this in a list, right, with a car and a cooter, and there's the car of your list, and here's the cooter of your list. And then there's a value for the root. You guys did it, right? Give me a big nod. Yeah? Thumbs up. Okay. Not fingers up. Not that finger. Thumbs up. Yeah.
Is it a complete binary tree?
Not necessarily. Just the binary tree with, in any case, it's got a binary tree on the right and a binary tree on the left. So here's a program to sum up the nodes in a binary tree. Call the program again on the left subtree. Call the program again on the right subtree. Add the two answers together, and then add 1. Everyone agree? So here's how I'll write it. To sum up the nodes in a binary tree, sum up, let's call the tree T, sum up T dot left, sum up T dot right, and add 1. And return this. This is not Scheme, it's just some kind of pseudocode. But these two things mean recursive calls. These two things mean do whatever you have to get the left subtree. This would be a car, this would be a cooter. Add them together, add 1, there's your answer. How do we know this works? We'll prove it by induction.
So we're interested in the number of nodes, not the actual sum of the values of the nodes?
Right, just the number of nodes. Let's prove it by induction. Let's assume that sum T left does what it's supposed to do. So this returns to us by induction, because it's a smaller tree, the number of nodes in the left subtree. Okay, that I get for free by my induction assumption. Similarly for free, since this is a smaller tree, this is going to return to me the number of nodes in the right side by induction. How do I get the number of nodes in a tree? I take the left nodes, the right nodes, and I add 1 for my root node. This plus that. End of proof. Every recursive algorithm has an induction proof on its correctness. All you have to do is show that the gluing that you do to get your final answer makes sense. And you'll know you'll get the right answers for the recursive solutions by the mathematical induction assumption. The same way when you write this, you know it's going to work. You have this leap of faith when you write recursive algorithms that the recursive calls are going to come back with the right answers. That's why, and I was wrong about this, that I thought if you do Scheme first and you spend a whole month doing nothing but recursion, that you would have completely internalized the idea of mathematical induction before you even saw it. And I was wrong. It's not true. I'm not sure why it's not true, but it's not. But mathematical induction is sitting here. If you can write a recursive algorithm, then you've already thought of the mathematical induction ideas. You're assuming these smaller cases work, and that's how your algorithm works. Yeah, question?
Do you at some point I mean, what you haven't really done is prove that the base case works.
I didn't prove the base case works. You're right, Sharon. I left it out, and my proof wouldn't be right unless I did.
Okay, so in the real world, you would actually...
But in the real world, my program would actually have a base case, and here I didn't put one in. There should be an if here that says, you know, if there's no car and no coulter, if there's no left and right subtree, then just return 1. And actually, I'd have to be more careful. I have to say, if there's no left subtree, return 1 plus the right subtree. Okay, if there's no right subtree, then return 1. I have to do it in steps.
Do you consider the things at the bottom a node?
Yes. Yeah. You mean, leaves are nodes. They're just special kinds of nodes. Yeah. So you want to count them. All right, questions about this? The answer is you should always.
Okay.
There's no reason not to. And I don't know why they don't just teach induction from the beginning. And in fact, if you're really concentrated and you look at my notes back at the beginning, I don't make any effort to show that you go from n to n plus 1. I say you go from the smaller cases to the next bigger case. And that's what strong induction is. So I don't think you should separate the two ideas. I think it is better just to be presented as one idea. But some of you are probably thinking, what, 2 ideas? What is he talking about? There are 2 ways of presenting induction. One way is assume it's true for n, show that it's true for n plus 1. Okay? The other way is assume it's true for everything, n and all the smaller cases, and show that it's true for n plus 1.
And which one is called strong?
The strong one is where you assume that it's true for all the cases. And in general, you don't have to pay any extra to get all the smaller cases. You get them for free. As long as you have a base case at the bottom, you get all the smaller cases for free, and you might as well assume they're true. But sometimes you have to use the strong induction idea. In this case, for the binary tree, we have 2 smaller cases, neither one of which is size 1 less than what we started. They're both half the size of what we started, possibly. So you have to use strong induction there. So in general, I think it's better to just think of induction as an idea where you want to show that it's true. I always just pick an n. I want to show that it's true for n. I'm going to assume that it's true for all the smaller cases, n minus 1, n minus 2, and all the other ones. I don't like to reach toward n plus 1. I like to reach toward n and assume that it's true for all the smaller cases. Okay, that's my own personal way to look at it. Yeah. Brian.
In the case, though, that you're pulling out, when you pull out n, it has to be an arbitrary member of the set of the cases, right? So it can only be true if all of the cases are true to begin with, right? I mean, otherwise, if you pull an arbitrary one out, there's a chance you might get one that doesn't.
I'm not sure I understand the question. When I take n out, it is an arbitrary n. But I get for free by induction that all the cases smaller than this arbitrary one that I pulled out already work.
Down to some base.
Down to some base, right.
It could be 6.
It could be 6, right. Down to some base.
Okay, yeah.
Right. Is it? Okay. Yeah, Chris.
I remember once thinking, maybe saying that, and it made a lot of sense at the time. Still kind of does. It seems like it should only be true that that it's true for all cases down to...
Can we videotape this and just put it on the web as Chris's musings? And we'll have 4 million hits, and people all over the world in Korea and Japan watching Chris goes, today I thought about something which I think is true and which I no longer, but it could conceivably... All right, get to the point here.
Working on it. All right. So it seemed like it was true that down to the number of base cases of steps below n, that was all you could assume. Because don't we have to prove... Like we have the one base case, we have to just prove a step from 2 connected, like 2 consecutive cases, so that we can step from our base case to wherever. When we've got 6 base cases, then we can assume it's true for up to 6 below where it is, and then we prove it's good to go. Is that all still weak enough?
It's a great question. This is a question that Doug was asking me earlier. Let me address this question because it's fundamental, and a lot of people are saying, well, how do you know like if there's a flaw in a proof? Where does it go wrong? And there are all subtle ways, and can you give us like a list of these ways? So the bad answer is, or the unfortunate answer is there is no list, and there is no check this, this, or this. But I know what you're talking about here, and I want to address it because it's important. Chris is referring implicitly to a problem that I had on one of the earlier exams that looks like this. I forget what it looks like now. Something like this. Is this true? Do I have it backwards? Is that true? Is that right or not right?
That's right.
That's right.
Okay. Okay, this is an algebraic tautology. It's true. Now, there's also a base case when n is 0. A to the 0 equals 1. So here's a phony inductive proof. I'm going to try to prove that a to the n equals 1. I'm going to assume by induction that all of the smaller cases work. So here's n minus 1, here's n minus 2. 1 times 1 divided by 1 equals 1. Here's the base case, a to the 0 equals 1. And therefore a to the n equals 1. So there's a flaw here. There's nothing wrong with this algebraic equation. There's nothing wrong with this base case. So where's the flaw in the whole big picture? The flaw in the picture is that
The minus 1. The denominator. You haven't defined it.
this here,
Yeah, it's a to the minus 1. Where have you defined a to the minus 1?
It's the flaw.
When
When n is 1, you have
oh, when n is 1, right, right. So when you write an inductive proof out, you have to make sure that your argument is really a general argument, that it works for every single case bigger than your base case. Right? Sometimes, if somebody expresses an argument to you in general and it works for an infinite number of cases, you tend to be convinced. And then you miss the one case that it doesn't work for. This argument doesn't work in general for any value bigger than 0. It works for every single example except the case when n is 1. When n is 1, this says that a to the 1 equals a to the 0 times a to the 0, that's fine, divided by a to the minus 1. There is no a to the minus 1. And if there was, we'd have to have another base case for it, because it doesn't exist.
Although what happens if we factor that, the right-hand side of that upper equation out?
Here's another proof.
We could simplify it so it doesn't have to.
Here's another proof. A to the 0 is 1. A to the n equal a times a to the n minus 1. Each of these are smaller. Right? A to the n minus 1 is smaller than n. 1 is smaller than n. So they have to both be equal to 1. How come this proof doesn't work?
Where's a to the 1 times a to the n? That's
right. A to the right. If you just write a to the 1.
Let's go into your magic world.
Oh, my magic world of right. But I'm trying to fool you here. So okay, I'm trying to fool you. What's wrong with this proof? I could have.
You haven't defined it.
No, not this time. It's not the problem. Here's a to the n equals a to the 1 times a to the n minus. Back up. In this proof, the problem was that for one of the cases that I claim this general argument works for, it really doesn't work. I hid that in a general argument, but it doesn't work when n is 1, because this turns out not to even make sense. You can say I could fix it if I add another base case, but that's not going to happen unless there was another base case, and there isn't another base case. But you don't necessarily need a second base case just because these two things use, that's really your question. Do you need two base cases when this uses two subproblems smaller than 1? The answer is yes, only when the general argument will force you past this base case or underneath it. And what we did before, the two trees.
Doesn't it automatically force you past the base case if it's referencing -1 and -2?
Yes, that would, but doing it in half wouldn't necessarily get you past the base case, right? If you start with 8 and this depends on either 4 or 3, that's not necessarily going to get you past your base case. And in fact, the Josephus problem is j of 2n in terms of jn, right? You only need one base case for that problem because they all get held up by the bottom by Atlas, n equals 1, and it never gets past there. All right, so you don't always need lots of base cases just because you have your problem based on two different subsets. It's only when those things eventually will pass up that one base case that you're hoping is going to be the foundation.
With the multiplication or division, with these like divide and conquer kind of thing.
Mm-hmm.
You can't,
When they're divided,
you can't skip the base.
you can't skip when you have divide and conquer. You can skip when you have negatives, when you have subtractions. Yes. Good question, Chris. Yeah.
If you write your recurrence equation like that with n minus 1.
Like this? Yeah.
Then that screams for 2. Right.
Good.
It does not necessarily is the most efficient way to write this recurrence
Right.
relationship. But if you write it like this,
If you write a recurrence relation that says, t of n is multiply t of n minus 1 times t of n minus 1, divide it by Tn minus 2. You better have two base cases there, or sooner or later you're going to go past
So
it.
in this case, I would say what's wrong with it is that you don't have the second base case.
It would be fine to say you don't have the second base case, or it would be fine to say that the argument doesn't work for n equals 1. Somewhere along the way you have to say that the argument does not generally hold, assuming this is your only base case. But I agree, you could write it that without being equivalent.
Okay, so
Just as
There's
good.
a difference between this and that, because here...
A big difference between these two. Right, there's a big
What's
difference.
missing is the second base case.
That's right. What's missing here?
What's missing is that the base case is selected.
Definition of A to the Y.
Yeah, Chris.
There's nothing missing there.
Nothing missing? This is true?
Yeah, a to the 1 is a times 1. A to the 2 is a times a to the 1.
A to the 1 is never proved.
No, but you can't prove a to the 1. It doesn't matter.
Oh, so you agree that a to the n equals 1 now?
No. But
But-
a to the 0 is 1.
Right.
A to the 1 is a times a to the 0.
He's trying to prove A to the Y.
I'm trying to prove that a to the n equals 1 again.
Right, but that proof doesn't show that. That proof shows
That's true.
that
It doesn't. Of course it doesn't, right, because we know it's not true. But why doesn't it? So what's wrong with this proof, maybe that's what you're trying to say, is I have this base case, I have this thing that's true. Each of these are two smaller cases, therefore they should be 1. Stop me there. That means n minus 1 is always smaller than n, and 1 is always smaller than n. So they're two smaller cases. And 1 is always smaller than n. Throw a tomato. 1's not always smaller than n, right? N could be 1, and then 1 is not smaller than 1. That's where this argument gets killed. If I gave you this proof, the only real way to say this one doesn't work is to say, you are giving me an argument here that is not true for every n bigger than 0. It's only true for n's bigger than 1. So either you give me an argument for every n that's bigger than 0, including 1, or I keep the same argument you have that works for any n that's bigger than 2, and you give me a base case for n equals 1. One or the other, but you can't have both angles
The
here.
base case isn't inside the domain for which this is true, right? I mean, this is true for a larger than 2 or whatever.
This is true for n bigger than 2, or equal to 2. It really is true for n bigger than or equal to
And our
2.
base case isn't in that. It is not inside that. So that's
Well, that's one way to look. Right.
right.
The inductive idea here works for n bigger than or equal to 2. The inductive idea fails because I can't claim that this 1 is going to be smaller than this n for every single n unless n is bigger than 2. So this inductive idea only works when n is bigger than 2. So I leave out a case.
But your base case doesn't have to be in the inductive. Your base case, like Fibonacci, the base cases for Fibonacci are not in. You can't get them out of the Fibonacci formula.
That's true. That's true. You did, right.
But they have to be within the range for which the equation is true.
No.
But doesn't this thing to me show why you don't teach strong induction?
Sorry, Jacob.
In my opinion, this shows
Yeah.
exactly why you don't teach strong induction. Because both of these, if you use the other induction, it'd be very clear to you what was the problem. But using strong induction, you have to be much more careful. And that's why.
Oh, I see. If you don't use strong induction, you just say, well, this doesn't even have a chance, period.
Yeah.
Maybe so. Look, there's a lot of pedagogical reasons why people teach induction by doing the n to n plus 1 way. Here's the reason most people do it. It's because it's kind of easy to teach people how to prove some formulas with induction. Here it's true for n, plug it in for n equals n plus 1, and then try to make the algebra work. And I have seen people do 15 of these and have no idea what proofs by induction are. So I hate doing it that way. I always start with different examples. And maybe it works that way. Maybe you need to do 20 of these sums, and then you do get what induction is. But I've seen too many people try 20 of them and still not get the idea. So I like to kind of do a lot of different examples outside of sums. And even then, it doesn't always work. But I don't know what works. I'm still plugging. Another tree problem. A tree of height n has less than or equal to a binary tree. Yes. An organic tree of height n has less than or equal to 2 to the n leaves. The first thing I have to do is tell you what height n is. Here's a tree of height 0. Okay? What's the height of this tree? 1, 2. The height is basically, or the depth, depending on how you want to look at it, is the longest path from the root. Okay? So this guy's got this is a 2, this is a 2, this is a 1. The maximum of the length of all the paths. That's another way to look at it. Everybody get what the height is? That's what I mean by the height of a tree. A tree of height n has no more than 2 to the n leaves. And you can kind of check this. I mean, the most leaves you can get is if you spread it out into a complete tree. So here's height 2, and height 2 has exactly 4 leaves. So you get equality when it's a complete tree, but you get less than for any other subsets of that. Joe, you have a question? All right. So we're going to prove this by induction. And we're going to do it in 2 different ways. One way, which goes from, say, n to n plus 1, and one way that does it by strong induction. And they're really very different proofs, and they're both very short and painless.
Now, with strong induction, you're typically going to n, but the difference is not that you're going to n versus that you're going to n plus 1.
I like to focus on the thing you're trying to get to rather than the assumption you're trying to work from.
Maybe if in this you said you're going to do it both ways, maybe if we do it to the same spot in both ways, that
we will.
Can compare and see.
We will. All right. So I want to show that this is true. And I'm going to assume that it's true, first of all, for a tree that has height 1 less. Okay, I'm going to assume that it's true, first of all, for trees of height n minus 1. Assume true for trees of height n minus 1. Okay, that's one way we're going to do it. Let's do it this way. All right, I got a tree. It's got n for its height. I want to convince you it's got less than or equal to 2 to the n leaves. I'm going to try to take this tree and fiddle with it so it'll be a tree of height 1 less. Then I'll use my inductive assumption, and I'll try to argue about what happened as I went from my tree with height n to my tree of height n minus 1 to show that I still get 2 to the n leaves. So I'm going to take the tree I start with that has height n, I'm going to knock it down to a tree that has height n minus 1, use the inductive assumption, and then work my way back up to show what happened in that process to show that I get no more than twice as many leaves. Right, that's the plan. How do I take a tree of height n and cut it down to a tree of height n minus 1? If I cut it in half, I'm not going to get 2 trees of height n minus 1. If I cut it here, I might get 2 trees of n minus 1. I might not. Yes. If I take off all the leaves, what happens? Then every single path from the root to the bottom just went down by 1, including the maximum path. So I can take off all the leaves. Take off all the leaves from the tree you start with, and the tree that used to be height n is now height n minus 1. Right? So I'm going to prove this is true. Take off all the leaves. The resulting tree has height n minus 1. Okay, why? Because every single path from the root to the bottom has now gone down by 1, including the maximum path that gave me height n. The resulting tree has height n minus 1. By induction, how many leaves does this thing have? By induction, this tree, the new tree, has less than equal 2 to the n minus 1 leaves. Okay. Where do I go from here?
It's a binary tree.
Add at most 2 leaves.
If I went back now and put back the maximum number of possible leaves, 2 on every single one that remains in this tree, how many leaves would I have in the new tree? Twice this many, right? 2 for every one of these. So I'd have 2 to the n. But that tree has got to be at least as big as the one I started with, because it's got all the possible leaves put in. I took them all off. There might have been 2 on each branch. There might have been 1 on each branch. So I took them all off the first time, but when I put 2 back on each one, I get a tree that's bigger than the one I started with. So add back 2 leaves to each leaf, and you get a tree which is bigger or equal to our original. Bigger or equal than our original. Blah, blah, blah. I'm actually writing this out formally, which I hate doing because you can't read it anyway. I just like saying it in English. Add back 2 leaves to each leaf that's here. You get a new tree that's at least as big as the one you started with, because you're adding the maximum number of leaves to each remaining leaf. This new tree has at most, this new tree, which is bigger than what we started with, has at most 2 times 2 to the n minus 1 leaves, because you add 2 for every leaf that's there. And that equals 2 to the n. So this bigger tree we have has smaller than 2 to the n leaves. Certainly a smaller tree is going to have less than 2 to the n leaves. And that proves the induction. Yeah?
I got a couple questions.
Yes?
First one is
21.
The new tree you said has less than or equal to 2 to the n minus 1 leaves. You should actually have 2 to the n minus 2 leaves, I think, because a normal tree has 2 to the n minus 1 leaves. Height being n.
Start counting at 0.
No, this is height. This is height 2.
Oh, okay, never mind.
Okay? So
So one node is not height 1.
one node is height 0.
Okay,
Right.
sorry.
Right. Right. But if I did redefine it in your way, the proof would all work. Just everything that was n would turn to n minus 1, and everything that was n minus 1 would turn to n minus 2, and the same idea would work.
So, and you're also saying that when you add back 2 leaves to each node, you automatically get a tree that's bigger
Sure.
than the original?
Right.
What if the original had all its leaves?
Then bigger than or equal. Bigger or equal. That says
Oh,
bigger.
that says or equal.
Yeah, well.
What if by
It does.
removing that leaf, you remove the stem and then...
You can't get more than adding 2 leaves to every tree. And that was the worst it could have been. There's nothing to this recurrence recursion. Basically, you know, when you go to the next height, the worst you can do is double the leaves. So that's why you only get a factor of 2 more. But there's a completely different way of proving this. Yeah, Bar.
Isn't it simpler just to start with a tree of n minus 1 and add the maximum number of leaves to it and just go there rather than going back and forth?
Now, is this,
You know
is
the,
this
you know
weak
the maximum
induction or
number.
strong
You
induction?
know the maximum number of leaves.
All right, so let's start with any arbitrary tree that's height n minus 1. You want to show that any tree of height n has double leaves. So then you have to argue that in order to get a tree of height n, it means you have to add a leaf to a leaf here.
This is double the number of leaves. The maximum number of leaves that
Right,
you add is
right.
2 times the
Yeah,
number.
I think if you actually wrote it out, it would be a little bit tricky, because in order to go to the next height, you have to specifically say you're going to put nodes on the leaves that are height n minus 1 from the top. You could do it. You could do it forward too. You can do it.
Now, this was weak induction, or?
This is weak induction, because all we do is assume that it's true for the n minus 1 case.
Okay.
But now we're going to do strong induction. And I left out the base case here. You can check the base case works. Here's strong induction. Here's a tree. I want to show that it's got at most 2 to the n leaves. Here's the normal way of doing recursion on trees. This is the weird way. This is the normal way. You got a left subtree and a right subtree. They're each smaller than the original tree. Therefore, they each have height
No more than 1 less.
no more than 1 less, right? Because you're getting rid of 1 from each of the paths from the root down to the leaves. Each of these, if this is height n, then this guy and this guy cannot be height n. They have to be smaller. If either one of these was height n, then this would be height n plus 1, and it's not. This is height n. So these have to be at most height n minus 1. So each of these has at most 2 to the n minus 1 leaves. Well, how many leaves does the whole thing have? 2 times this, because the number of leaves in the big tree is just the number of leaves in the left plus the number of leaves in the right. So 2 times that is 2 to the n, and that's the proof. This proof is easier. And this is strong induction because we don't know the size of these 2 subtrees. They could be much smaller than the original tree. They could be half of it. Right? So that's a more natural way to prove things about trees. And that's a more natural way to do algorithms on trees. You almost always split the tree into 2 equal parts if you can and do an algorithm on each one.
If you take your tree that's thrown up on the right side of the left board,
Yeah.
if you remove the lower left 2 nodes, so it just has a single branch coming off of the left, you go the picture to the right of that, and remove the 2 lower left nodes, so it's just a short branch on the left side.
2 lower left? You mean this one and this one?
No. Two bottom that.
Yes.
Bye-bye?
Bye-bye.
Okay.
So then when you go to apply your weak induction,
But we can't because it still has height 2.
it still has height 2, so we remove all.
You have to...
No, we're just starting. That's our starting tree.
Oh, it's your starting tree.
Yeah.
Okay. So now you remove all the leaves.
Remove all the leaves. And
So now it's height
if you
1.
want a leaf, don't you remove that?
Oh, yeah, you remove that too, right?
So now you go and you add 2 leaves to each leaf, but there's no leaf on the left, is there? It's just a node.
That's a good point.
If you've gone back to the root, what constitutes a leaf?
The argument still holds, but I didn't carefully describe it. Chris is right. There's something strange that happens if the leaf that you took off is actually connected to the root. It doesn't make it any worse because you can only add 1 more here. You can't add 2 more. So nothing changes in the argument except that I should mention it because maybe something might have changed. That's a good point. I could say add the maximum number of leaves possible back, and it's no more than twice as many. But you're right. You're right. That's a special case.
And it doesn't seem in the strong.
You don't have to do anything. No, the strong induction, right. It's much easier to write this proof down. It's much faster. Brian.
It seems like there's another sort of minor problem that might pop up. If you try to take the n-1 tree of a 0 height tree, it just doesn't make any sense, I think, to talk about a -1 height.
Oh, but you wouldn't go from a 0 tree to 1 less, because that'd be our base case. Right, so that wouldn't happen. We would stop at the base case. And what you're really saying is I didn't say what the base case is here, and I should have. The base case is when it gets to 0 height. That's 100% right. That's true.
Can you verbally explain the strong one again?
Yeah. You take a tree of height n. A tree of height n is made up of the root and the 2 potential subtrees. Either one of these could be empty. It doesn't affect the argument. By induction, each of these subtrees is 1 height less than the original. It can't be the same height of the original because then the original wouldn't have been n. So each of these subtrees is n-1 height or less. Therefore, each of these subtrees has at most 2 to the n-1 leaves by induction. And if we add them together, we get twice that many leaves, which is 2 to the n leaves.
Plus the one on top.
No, that's not a leaf.
Oh. Okay.
Right? We're not counting the nodes now, Gary. We're just doing leaves.
Okay.
So it's just left plus right. If we did have to add the top, this would crash like a lead balloon. Right? The whole thing wouldn't work.
So if you add them back together, then together they have less than 2 to the.
Less than or equal to 2 to the n leaves.
2 times 2 to the n-1.
Right, it's 2 to the n. Right. Make sense? Yeah.
Why is that
Michael.
strong? Because you're saying n and then you're
Because
saying
these guys are not n-1. These guys. Oh, I take it back.
No, they could be n-1, but they don't have to be.
We don't know for sure that they. Right. This one could be n-3, but the point is, whatever it is, it's going to be smaller than 2 to the n-1. Right. So they might be smaller height trees. We know one of them is n-1. That's for sure. Otherwise, that would never be n. Okay. Other questions? All right. You're too tired. I can't do any more. And what I'm going to do is I have an important induction proof that is on number theory that I'm going to throw into the recitation. I'll have Tara do that, and she's going to show you how to do it. It's the one with ADU ball. She's going to show you how to solve any of those by induction, and much more than that, she's going to show you how to get the numbers that work, and how to construct an induction proof kind of by construction and create the numbers that work. And we're going to go into that problem in much more detail and solve it completely on the last week of the course. So I want you to see that induction proof in recitation. And then you can ask any questions you have in recitation on the problem set.